I feel like spring break needs to come like 1 week earlier than it does. I just came from 520 and it was like half the people were there when one class started. They filtered in eventually, but it's like we have a similar situation here. You'll have a good weekend. Okay, let's get started. So today we're going to look at a couple of constructions that produce graphs with large chromatic number, and in particular, like ones that have that do not have large clicks. So look for and without large clicks. So we had already just a lower bound, so let's just recall that the chromatic number of a graph is greater than or equal to omega of G, which is the size of the largest click in the graph. And the reason for this is because if we look just at the click, since every vertex is adjacent to every other vertex, we require at least that many colors to color just the click part, and then there may be other stuff going on in the graph as well. So that's where this lower bound on the chromatic number comes from. And right now we're just going to focus on how bad can this bound be and in what ways does it fail. So just for starters, if I give you a graph G, how can you construct a graph that has larger chromatic number? Like, what's the easiest possible thing that you could do? So how do we construct a G prime with chi of G prime larger than chi of G? Yeah.
Connect a new vertex to every vertex in G.
Yeah, so I could just say like whatever my G is here, let's say it has some vertices, then my G prime, I would just add a new vertex and connect it to every vertex of G. So in G prime, add one vertex, connect to all vertices of G. So this for sure has larger chromatic number because however many colors we needed to color G, now I have this other vertex that's connected to every vertex of G, and so I'm going to require an additional color to color that vertex. So one observation is that this construction is going to produce a lot of triangles. Which is bad if we want to produce large graphs without clicks. So I guess like, what does this have? This has a lot of triangles, but it also, whatever the size of the largest click in G is, we've made a new click of size 1 larger. So may contain large clicks. So one thing we're gonna try to do now is give a construction for making graphs with successively larger chromatic numbers, but without any triangles in them. So there will automatically not be any large clicks in there, right? Because if you're triangle free, then the largest click has size 2. So our goal is to construct graphs with the largest click having size 2, so triangle free, and larger and larger chromatic number. Okay, so let's see a definition, which is a construction that will achieve this, and then we'll prove why it does this. So we have a definition. So given a simple graph G, we'll have this thing called my Chelsea's construction. So And this is gonna produce another simple graph that contains G. And I'll call this one G prime. So I'm gonna suppose G has vertices V1 up to Vn. And then G prime is gonna have vertices V1 up to Vn, and then also U1 up to UN, and then an additional vertex called W. So G prime has, so we keep V1 up to Vn, and then we're also gonna add in U1 up to UN and some other vertex W. So this is for vertices. And then for the edges, we're gonna have W be connected to every U. And then each U sub I is gonna have edges to the neighbors of V sub I. So U sub I gets edges to the neighbors of the corresponding V sub I. So let me do an example. So let's just start with P2 as our G. So it looks like this. Then to do the Michalski construction, I'm gonna add, so here I'll label these. So this is V1 and V2. So then I'll get U1, U2, and W. So W gets connected to all of the U's. And then U sub I will get connected to the neighbors of V sub I. So for example, U1, well, we look at V1, V1 has an edge going to V2. So then I'm also going to draw an edge going to V2 from U1. And then same thing for U2. So basically the U's are like a twin set of vertices to the V's. They get all the same adjacencies. And then in addition to that, there's the W that connects to all the U's. Okay, so what happened to the chromatic number in this example? Yeah,
I think it's always gonna go up by one, just because we're creating the same adjacencies even though we're like adding over. It's like kind of what we did earlier, but without creating clicks, because we're like.
yeah. Yeah, so like, yeah, so in this specific example, like we had something with chromatic number 2, and then it went from 2 to now we're looking at the 5 cycle. We know that odd cycles have chromatic number 3, so it went up by 1. Yeah, and that's always gonna happen, so we'll prove that. Next, let's do one more example. So I'm gonna ask you all to draw so do C5 as an example and draw the Michalski construction for C5. And yeah, also think about what the new chromatic number is. Okay, so this was the drawing that I got. Does this agree with what you all? Yeah, and then what about the chromatic number? Yeah, so why is it 4?
Well, you have the original 5, which have chromatic number 3, and that kind of forces your hand with the 5 you add.
Yeah.
And you have the last one, which goes to 4.
Yeah, so this is gonna have chromatic number. So chi of this G is equal to 4. Yeah. Okay, so hopefully this is giving you kind of a feeling for how this construction works. So let's prove the theorem about this. So this is basically just saying that this construction accomplishes what we had hoped. So it says that from a K-chromatic triangle-free graph G, Michalski's construction produces a K+1 chromatic triangle-free graph G prime. Okay, are there questions about the statement? So let's do the proof. So let's let the vertices of G, let's denote those by V's, so V1 up to Vn, and then we'll let G prime be the graph produced from it by the construction, and it will have the vertices labeled the same way as we did in the definition. And I'm gonna denote by large U just the set of the U sub I vertices. Okay, so first of all, why is G prime triangle free? We see why that's true. Yeah, Marcus.
Because none of the views connect to each other, but we also have that none of the views connect to each other. This is the original one. The only connection.
Yeah, so how could we have produced a triangle? So let's suppose, yeah, so like just looking at this, like what are the possibilities for triangles? Well, all 3 of the vertices could have come from the V's. We know that's not possible because the graph is triangle free. If one of the vertices is this one, well, that's automatically not triangle free, right? Because this vertex doesn't connect to any of these. So that would mean that the remaining 2 vertices would have to come from U, but there's no edges between elements of U, and so on. So yeah, so we have to kind of like go through and make a case-by-case argument, but we'll see why it's not possible. So let's suppose XYZ is a triangle. So the first observation is cannot have all three in B of G. And the second observation, so the set U is independent, right? There's no edges between vertices in U. So that means that at most one of X, Y, and Z could come from U. So since U is independent, at most one comes from U. And then the next observation is that W cannot be one of these because it only has edges to U, but we already said at most one vertex comes from U. So W cannot be one of X, Y, or Z because so the fact that at most one of X, Y, or Z comes from U implies that there is at least one coming from V, right? And W does not connect to V. Okay, so now let's suppose, so the only situation that is left is that we have two vertices from V and one from U. So let's look at what if two are from V and one is from U. I'm sorry, I should write V of G here. Okay, so what happens in this case? Yeah,
U like only goes to the neighbors of its counterpart vertex, which can't neighbor each other. There would have been a triangle in the V's.
yeah, exactly. So whichever one came from U, so let's say U sub I is one of these. So U sub I connects to the neighbors of V sub I. And if those neighbors were in turn connected to each other, so that's like forming a triangle, then that would mean that there was already a triangle in V of G. So if there is a triangle, if there is such a triangle, then there would be a triangle in V of G just by replacing U sub I by V sub I in this triangle. Okay, does that make sense? Are there questions about this part?
You say that there was a triangle in V of G, or just say that there was a triangle in G? And then that's the contradiction, or does it not really matter?
I guess a triangle, yeah, so yeah, I'll just say that, yeah, I think that makes more sense, saying that there's a triangle in G. Yeah. Yeah, good. Other questions? Okay, so now let's prove why why it has a chromatic number k plus 1. So first, let's just see that G prime is k plus 1 colorable. So how could we take a proper K coloring of G and extend it to a K plus 1 coloring of G prime? Yeah,
We can color each UI the same color we colored VI, and then just assign a K plus first color to omega, or just no wait.
yeah, so yeah, exactly. So so given a K coloring of G, we'll assign the same color. So we'll give, or I'll color U sub I the same color as V sub I. So that should be fine because we already know that the edges from V sub I to its neighbors are good. They have the endpoints of those two edges have of those edges will have different colors. So then coloring U sub I, which has the same neighbors as V sub I, will work out. So we'll color U sub I the same color as V sub I for each eye. And then color W the remaining K plus 1th color. Let me grab this picture. So for example, if I have a proper 3 coloring of this cycle, then what this would do is just assign each U sub I the same color as the corresponding V sub I. And then we would use our 4th color on the remaining vertex. Okay, so this tells us that chi of G prime is less than or equal to chi of G plus 1, right? But perhaps it's possible to make some coloring by fewer colors. So let's see why we also can't do that. So are there, first, before we move on, are there questions about this part? Okay, so let's so to show that we can't have a smaller coloring, I'm gonna show that, so we'll prove that chi of G is strictly less than chi of G prime. So how are we gonna do this? I'm gonna take a proper coloring of G prime and use that to obtain a coloring of G by fewer colors. So the strategy is going to be to take a proper coloring of G prime and use this to obtain a coloring of G by fewer colors. So that tells me whatever the chromatic number of G prime is, whatever the least number of colors that I can use to color it, there actually is a way to color G using fewer colors. Okay, does the strategy make sense? So So I'm gonna let G be a proper K coloring of G prime. And without loss of generality, I'm gonna assume that the color assigned to that last vertex W is the kth color. So why is this without loss of generality? We could just rename the colors. Yeah. Okay, so that means that on the set U, we only use the colors 1 up to K minus 1. And then possibly on V of G, we use all K colors, right? So what we want to do is change out any that had that kth color for something that is in the first K minus 1 colors. So maybe a picture would help. So let me draw this guy again. Okay, so let me do a proper coloring where maybe we use one of these. Uh, oh no, I forced myself to use red here. I'm struggling to actually produce an example that here.
Wait, why can't that last one? Does it have to be there?
So I think, okay, yeah. So what I want is, I think this is the easiest way to produce an example that has what I want. So let's say that so we had just happened to have colored a couple of these vertices red, for example. So like this is like the situation that we could be in, right? Like we may have used the kth color, which in this case is red, to color some of the vertices in V. Okay, so how do we remedy this situation? So on the vertices of G, we may have used the kth color. And we want to change that in some way to obtain a proper K minus 1 coloring of G. So we want to I'm going to say recolor these vertices using colors 1 up to K minus 1. So I'm going to let A be the set of vertices that have the bad color So let's let A equal the vertices V in V of G such that G of V is equal to K. Okay, so for each of these, so let's say V sub I is an element of A. I'm going to change the color of V sub I to, does anyone have a guess as to what we should change the color to? Yeah, so it'll be the color of the corresponding U sub I. Okay, and then we want to check that this is a proper coloring. Of the graph G, right? So we're trying to obtain a K minus 1 coloring of G, so we don't really care if it's proper on the entire G prime. So I'm just going to check the edges that are in G. So let's do like a case by case breakdown of what these edges could look like. So if my edge was between two vertices that are not in A, then it's already good, right? Because we didn't change anything. So if E is between vertices not in A, then it is already properly colored and nothing changed. Okay, what happens if the edge is just inside of A? So if E has endpoints that are completely contained within A, why is E properly colored? This is a trick question. So no such E exists, right? Because the vertices of A used to have, they all had the same color. So that means that there's no edges inside of A. So these edges don't exist. Because A is an independent set. Okay, so then the last case is if we have an edge with one endpoint in A and one endpoint not in A. So edges, let's say V sub I, V prime with V sub I in A and V prime in the vertices of G minus A. Okay, so why are these edges properly colored? Yeah.
Is B, okay, BI is in A and B prime is its neighbor.
Mhm.
Then because we already had a proper coloring, the vertex UI, which was also connected to B prime, cannot have the same color as it, so.
Yeah, so since VI and V prime are connected, that means UI and V prime are connected. And so that means that the original coloring that we had colored U sub I and V prime different colors. So that means that we're good because this is the new color of V sub I. Okay, so are there questions about this? So this gives us a proper K minus 1 coloring of G. And that finishes the proof. Okay, are there questions? So what is the upshot of this? So if we start with G equal to K2 and iterate the construction over and over again, then we'll get a sequence of graphs that are triangle free and have larger and larger chromatic number. Okay, are there questions? Okay, so we're gonna switch gears a little bit and talk about Turan's theorem. So this looks at the question, what are the smallest and largest K chromatic graphs with n vertices, where I guess you're measuring size by number of edges. So what are the smallest and largest K chromatic graphs with n vertices? So if we know the graph has n vertices and is K chromatic, then what can we say about the number of edges? Okay, so let's start with this proposition. So what is the least number of edges that we could have? Is what this is going to address. So it says that every K chromatic graph with n vertices has at least K choose 2 edges. I'm going to give you a few minutes to think about why this is true, then we can discuss the proof after. you have a idea for the proof?
So I'm thinking if the graph is k-chromatic,
Yeah,
then there's some like ordering of the greedy algorithm, the whole k color,
uh-huh,
but we use k colors.
uh-huh,
And for the greedy algorithm to like have to use k colors, like, at some point you're gonna need a vertex connected to at least one thing to use your second color.
mhm,
And at some point you're gonna need a vertex connected to two things to use your third color.
yeah,
And so on and so forth. You need at least 1 plus 2 plus 3 dot 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 plus k minus 1 edges,
yeah,
and that sums to k choose 2.
yeah, I think that's a good way to think about it. Did you have another?
Yeah, I mean, the way I thought about it was just like, that's so many combinations, like, of the K colors between the endpoints of the edges.
Yeah,
If you have like two colors that are never on like two endpoints, then they're never adjacent, so they might as well be the same color.
yeah,
It's gonna be like all the combinations of Ks to them.
yeah, yeah, I like both of these arguments. So like, yeah, okay, so let me write down what Marcus just said. So if we take so should we phrase this? So yeah, so what is K choose two? It's the number of ways to pick two things out of K colors. This is saying like basically for every combination of two colors, we need an edge that has both of those colors. And why is that? If we did not have an edge for one pair of colors, then there's nothing prohibiting those two color classes from just becoming one color class. So so for every pair of colors, we must have an edge whose endpoints have those colors. If not, we could color, or I guess we could merge those two color classes. To get a K minus one coloring. Does that make sense? Okay, so what about how do we get the most edges? So this was the least number of edges that a K chromatic graph could have. What is the most edges? So maybe we should do a small example. So like, for example, what if n is 6 and k is 3? So I'll just let you play around with it and see what the most edges is, and then we'll discuss.
Last proposition is short, but it could give us a k complete graph.
Yeah. Okay, what did you all come up with as the best graph for this case? So I guess we know we need 3 different color classes where each color class is an independent set. And then somehow we want to create like the most vertices in between, or sorry, the most edges in between these 3 classes. So what's kind of the best option? Yeah,
This is what they try to find.
yeah. And how many vertices should I put in each? Yeah, so if we put 2 vertices in each of these, and then I'm just gonna make every possible connection between these, so. Okay, I think that's all of them. So this is gonna have the most possible edges. And you can think about, I feel like we've done arguments like this before, but like, what if I moved this vertex out of the yellow class and into the blue class? I keep the same number of edges to the green vertices, but I lose these 2 edges and only gain 1 edge. So that would like decrease the amount. So like kind of distributing them, this is like a very loose argument, but distributing them around equally into the color classes is gonna optimize the number of edges. So okay, yeah, so let's make a definition. I don't know, have we already defined complete multipartite graphs? I don't think we have, so I'll write down the definition. So complete multipartite graph, which is written as k n1 up to n sub little k. So this is a graph with this many vertices, n1 plus up to nk, where the vertices are partitioned into independent sets of sizes n1 up to nk, and you add in all possible remaining edges, so then connect vi, or sorry, let's say we'll connect a vertex v with a vertex u if and only if they belong to different sets. So for example, this one that we drew here is K2, 2, 2, because we have 3 independent sets, each of size 2, and all possible edges outside of those independent sets. And then in particular, the Turan graph which is written TNR, is the complete R-partite graph with n vertices whose partite sets have size ceiling of n over r or floor of n over r. So this is like the one that just distributes the vertices into however many vertices there are into R partite classes that are of equal size as possible. So what is the chromatic number of a complete K partite graph? Sorry, I'll write chi of K n1 up to nk. Yeah. Yeah. So why is that?
Well, you have your like K independent sets, so those can be your colors, and then you can't have fewer because they're all connected by every other color.
Yeah, exactly. Yeah, so this is a K chromatic graph. And here's a proposition. So it says among simple R partite graph, or maybe I'll say this is, yeah, I'll say this, R colorable graphs with n vertices. The Turan graph is the unique graph that has the most possible edges. So going back to our example, what this is saying is that, for instance, in this case, the graph that we have drawn is the one that has the most possible edges. So if you want to make, say, a graph with n vertices and it's K colorable, then you just want to distribute them into partite classes that are as equal as possible, and then make it a complete partite graph with those partite sets. And that will give you the most edges. Okay, so I don't really want to prove this because I think the idea is very simple, and also it just gets hairy with counting the number of edges that actually occur depending upon what N and R are. So I think we should skip this in the interest of moving on to other things. So then there's one other kind of statement along these lines. So, let's just make the observation that if we have any more edges, so if we have any more edges, this would force the chromatic number to increase. So why is that? Let me go get the picture again. So if I added another edge to this picture, then so say I add one between the vertices, okay, so if I add an edge, it can no longer, there's no more edges that go between distinct partite classes, so it'd have to lie within one color class. And then if I do that, that will force those two vertices to need a different color. So now these need different colors now. So we saw earlier in the lecture, we saw graphs that had whatever chromatic number you like and no triangles, right? But those had like those had massive amounts of vertices to just kind of like space everything out that you needed. And what this is saying is like, if we fix the number of vertices and go beyond the maximum number of edges, then that will force us to use R+1 colors. But there's actually like kind of even a stronger statement that you can make, which is that it actually will have like a click inside of it. So here's the statement of that theorem. So among n vertex simple graphs, with no R+1 click, TNR has the maximum number of edges, this Turan graph. Okay, so let's look at this example again. So this was T6, 3. So that means that R+1 is 4. And so what this theorem is saying is that if I add an edge, then I'm going to have a click of size 4 in here. So let's see where we get that. So I added this edge. And then if I take these guys, so here's my click of size 4. Okay, do we see why this click exists? Yeah, so like, so if I add this edge here, then I have these two vertices, and I also have R-1 other partite sets. So if I just pick out one vertex from each of those sets, then I know well, for sure, these two vertices are connected to each other because this was a complete R-partite. And then I also know that each of these vertices is connected to the two vertices in the green class because of it being the complete R-partite one. And then I've also added in this edge between those two vertices. So that's where that click comes from. Okay, are there questions about this? I'm also gonna skip the proof of this, so that we can just like hit more topics. I feel like graph colorings have like so many interesting things to say. So I just want to like see the full breadth of like things that people study about them rather than like going into the details of every single thing. Are there questions? Okay, so there was another statement that I thought was kind of interesting about K-critical graphs. And this is going to relate things back to connectivity, which we were looking at a few weeks ago. So this says the following. It says every K-critical graph is K-1 edge connected. Maybe it'd be useful to remember what some of these things meant. So I think it's been a while at least since we talked about this, and sort of we haven't touched on K-critical all that much. Okay, so K-critical means that the chromatic number is K, but every subgraph has smaller chromatic number. So chi of G equals K, and every subgraph has smaller chromatic number. Okay, and then K-1 edge connected means that if I delete K-1 edges, then the graph remains connected. Okay, so let's prove this. Are there questions about the statement before we get into the proof? Okay, so for the proof, let's let G be K critical. And let's let XY be a minimum edge cut. And then what we want to show is that this minimum edge cut has at least K-1 edges. So the first observation that I want to make is that since G is K critical. We know that the subgraph just on the X vertices and the subgraph just on the Y vertices are K minus 1 colorable. Okay, so my claim is that this edge cut XY has at least K minus 1 edges. Okay, so how we're gonna prove this is we're gonna show, so we're gonna go towards contradiction and say, if this has fewer than K minus 1 edges, then we can make a proper K minus 1 coloring of G, which is a contradiction. So show if this has fewer edges, then we can make a proper K minus 1 coloring of G. Which is a contradiction. Okay, so here's how I'm gonna do this. So let's let x1 up to xk minus 1. These are gonna be the okay, so yeah, so okay, we have x1 up to xk minus 1 and y1 up to yk minus 1. And I'm gonna let these be the color classes of the proper colorings of gx and gy. Does that make sense? So this is the color classes of proper colorings of, and I should say proper K minus 1 colorings of GX and GY. Okay, so now what I'm gonna do is form a bipartite graph. H with vertices given by the X's and the Y's. And I'm gonna have an edge between an X and a Y if there's no edge between the set X and the set Y. So I'll just write it down and I'll explain. So we'll put x sub I, y sub j in the edges of H if there is no edge between the set x sub I and y sub j in the graph G. Okay, so why have I done this? So if this bipartite graph has a perfect matching, then I'm gonna get the desired coloring, the contradiction coloring. So and that's how, here's how this goes. So if H has a perfect matching, so let's just suppose for the moment that it does, then in G, I'll give color I to all of the vertices in Xi. And all of the vertices in the Y that it was matched to by the matching. In, let's say, in the Y sub j, that it is matched to by M. Okay, and then since there's no edges joining those two sets, just by how we defined the bipartite graph, this produces a proper k-1 coloring of G. So this gives a proper k-1 coloring of G. Okay, so I'm gonna stop there. There's a bit more to the proof. I don't like stopping in the middle of a proof because I feel like it's always hard to get back into it. But yeah, so we'll finish this up on Thursday, and then on Thursday we'll talk about the chromatic polynomial, which is like a really fun and cool topic. It's like one of my favorite topics in graph theory, so I'm looking forward to that. Yeah, I'll see you all Thursday. Hey. Amy.
I'm not gonna be here on Thursday. Do you do a lecture capture?
Yeah, so all of the lectures are recorded in Zoom.